Okay, so let us discuss about interrupt latency in this video. So what is interrupt latency? Interrupt latency refers to the amount of time the system takes to respond to an interrupt. Basically it means that actually whenever any of the hardware interrupts the processor for its, it needs attention of the processor to execute certain task. At that time actually how much the what is the amount of time that the system takes or the processor takes to respond to an interrupt. So this is important actually. The amount of time the system takes to respond to an interrupt means to answer the request call made by the hardware or any of the software inside the program. So at that time actually any of the um, attention that interrupt requires, the amount of time the system takes to respond to an interrupt. So that is what we call it as interrupt latency. So this time what we call it as interrupt latency. Interrupt latency is an important factor to decide the performance of a system. Basically the interrupt latency should not be too high also, because if it is taking too much amount of time to respond to an interrupt, then it is of no use, isn't it? Because if it takes too much amount of time means we are losing the efficiency of the system. So that is what. Now of course what are the factors that decide the interrupt latency? One is the longest period of time during which the interrupt is disabled. In the last video we discussed about disabling the interrupt. The disabling of the interrupt was done because the variables because of the uh, sharing of the variables between the task code and the interrupt service routing. Because of the data sharing problem we had disabled the interrupt. So when you are going to disable the interrupt, whatever the other interrupt comes, it has to wait. It has to wait till the earlier interrupt which was disabled. You need to enable the interrupt again. So how much the time is going to be elapsed before the enabling of the interrupt occurs. So the interrupt whatever that it had raised, it has to keep on waiting. So that amount of time that is lost, so that also gets added to the interrupt latency. So that is what you mean by this one, the longest period of time during which the interrupt is disabled. Next one what you have is this is whenever actually the higher priority interrupt. See, whenever there is a there are two more sorry 3 4 anything, okay, more number of the interrupts they occur at the same time. So when the more number of the interrupts occur at the same time, when you have the priority based interrupt. So priority means one interrupt you will have the higher priority, another interrupt you will have the lower priority. So you decide actually which interrupt you are going to service, because not all the interrupts you can service at the same time, isn't it? So one maybe the interrupt with the higher priority, that is going to be taken first. When that is going to be taken first, the interrupt actually with the lower priority, it has to keep on waiting until the higher priority interrupt is serviced. Maybe another interrupt actually maybe the medium priority interrupt. This priority interrupt actually the priority of the interrupt is lesser than this one, but definitely more than the lower priority interrupt. So this lower priority interrupt, it has to wait for this higher priority interrupt to get over, and also it has to wait till this middle priority interrupt get over. So it has to keep on waiting like that way. So that waiting period, what we call it as that is also gets added to the interrupt latency. That is what it has been written here, the period of time it takes to execute any interrupt routines for the interrupts that are of higher priority than the one in question. So the low priority interrupts they have to keep on waiting. So that waiting period, what we call it as the interrupt latency, it gets added to the interrupt latency. So last one that you have means of course the third one, whenever actually some interrupt occurs, the processor actually, if it is in the middle of the execution of any of the instruction, it is going to complete that execution, because when it resumes actually it has to know it will take the next instruction. Okay, so whatever it is doing, it will of course it will resume, it will finish the task, then it services the interrupt. So how much time, how long does the microprocessor take to stop what it is doing? Of course it takes some time to finish that execution of the task, and that time also gets added to the interrupt latency. Last one actually we have studied this one, isn't it? Saving the context and restoring the context. So saving the context means you push the registers, you push the register. So push the register, when you are pushing the registers onto the stack, so how much time you require to push the registers onto the stack, so that amount of time also gets added to the interrupt latency. Okay, so all these factors, they contribute to the interrupt latency. So basically interrupt latency means the amount of time the system takes to respond to an interrupt. So whenever interrupt occurs, so how much time your system takes to respond to it. So that is what you mean by interrupt latency. Okay, so let us discuss about one example that we'll take it here. Of course, maybe let me take one. Of course, this we have already discussed. Okay, so you have to let me take one example that you have to disable the interrupts for 125 microseconds for your task code. Means the task code and the interrupt service routing. The task code, for example, like here we had this task code. This is what you have task code here, isn't it? In the task code, actually, this variable, this we have discussed in the last video. This variable is being shared between the interrupt service routine and the task code here. So that variable actually, maybe let us assume that this amount, okay, whatever that happens, this high temperature of 0, it is going to be read from the hardware. Of course, the interrupt is raised by the hardware, it goes to the interrupt service routine. Then interrupt service routine, the value is taken. Similarly, the high temperatures of one value is also taken. Both will get stored in the high temp of 0 and the high temp of 1. The amount of time this taken, let us actually take out to be 125 microseconds. So this is why it has been written here, 125 microseconds for a task code to use a pair of temperature variables. It shares with the interrupt routine that reads the temperatures from the hardware and writes them into the variables. So same thing actually what it has been written in this code here. Okay, so similarly for this case also we discussed about one more code where the timer interrupt was there. So same thing actually you have the one is task code, another one is interrupt service routine. So this interrupt service routine, one is task code. Okay, so let me write this one. So one is task code you have, another one you have is interrupt service routine. So this task code and the interrupt service routine, whatever the time it is going to be updated. So let us take that disabling and enabling the interrupts. This is what you have to understand. First you disable the interrupts, then you enable the interrupts. So middle actually what the time is taken, that time. So example this I am shown here, the middle one, that it is going to take 124 microseconds for the temperature case. Similarly for the timer for updating the time, so it is going to take 250 microseconds. So you have to disable the interrupts for 250 microseconds for your task code to get the time accurately from the variables. It shares with the interrupt routine that responds to timer interrupt. Okay, so whenever some timer interrupt occurs, the task code, when it disables the interrupts, it goes to the interrupt service routine, takes the updates it time, then the updated time is stored in the hour, minutes and seconds. So that amount of time what it takes is 250 microseconds. So one thing, another one, the interprocessor interrupt routine, what occurs here. So interprocessor interrupt routine, so any of the other processor is going to interrupt the another processor. The processor which is working, the another processor is going to interrupt this processor for any of the attention that it requires. So that actually takes 300 microseconds to execute, and that the query that has been given here is that the processor must respond within 625 microseconds, that whenever after the raising of the interrupt request by the another processor, after raising the interrupt request by the another processor, the system has to respond with the 624 microseconds. This 300 microseconds is there. The only interprocessor interrupt routine takes only 300 microseconds. So you have the temperature interrupt routine, here it is timer interrupt routine, here it is interprocessor interrupt routine, and this interprocessor interrupt routine is going to take only 300 microseconds. So this buffering is given. So how much buffering is given? The buffering, total buffering that is given here is 325 microseconds. Okay, so whenever this another processor asks for the attention, that means it raises the interrupt request signal that has to be serviced within 625 microseconds. So let us actually go through and observe this one. What is the worst case interrupt latency that you get it here? So this is what worst case interrupt latency. What do you mean by this? What do you have in this diagram is, see for example, one thing what you have to understand here is that whenever actually let us assume that this is having the higher priority. Okay, let us assume that this is having the higher priority, that is the processor, the request raised by the another processor. So what happens here is that we know that actually, and one more thing what we'll assume is that the maximum, so okay, let me write it here, the maximum time that is taken, the maximum time for disabling the interrupts, the maximum time for disabling the interrupts is 250 microseconds. Okay, so the maximum time, that is the maximum time you can disable the interrupts. Means for this temperature routine, 125 microseconds if it is going to disable the interrupts here, isn't it? Because disabling and enabling, the time that gets elapsed is 125 microseconds. Similarly for the timer interrupt routine, let me write it here. For timer interrupt routine, the last problem, what did we have there? For timer interrupt routine, timer ISR, here also what was the case? 250 microseconds. And for this interprocessor, let me write interprocessor IP and ISR. For this one, what did we have? That is 300 microseconds, isn't it? So let me take one example here. Of course, whenever actually 125 microseconds, 125, so let me do the calculations here. Whenever actually 125, so and what is the time limit that you have? So for interprocessor interrupt routine, the time limit that is given here is 625 microseconds. 625 microseconds. 625 microseconds. Okay. So here what do we have? Now first let us actually take this one. Now 125 plus anyhow. So if 125 microseconds, first temperature interrupt routine comes here. Okay. So 125 comes here. So 125. Now now there are two interrupts which are being raised here. Okay. After this first one temperature routine, if 125. Now what is the timer interrupt it is going to take? Timer always is 250. Okay. So 250 microseconds. So 250 microseconds, this one takes 124 microseconds, this takes 300. Now when this comes 125 plus 300, so what do we have here? 125 plus 300, that will be equal to 425. We know that actually 425 is definitely less than 625 microseconds. So definitely this is temperature interrupt routine and this one is interprocessor interrupt routine. So this temperature interrupt routine plus interprocessor interrupt routine, servicing of that one, definitely actually both are going to take 425 microseconds, which is less than 625 microseconds. So there won't be any issue in this one. So definitely actually before the deadline, your interprocessor interrupt routine that will be answered. Means your interprocessor request will be answered. So interprocessor interrupt occurs, that servicing is done. So imagine actually if it is 250 microseconds. So one of the 250 microseconds which is there. So 250 microseconds plus 300. So plus 300. So that will be equal to 550. So definitely this is also less than 625. So it is not a problem here. So 250 plus 300, that is 550. So definitely less than 625 microseconds. So definitely it won't be any issue. So that also your interprocessor interrupt request that will be answered, isn't it? So that is how actually you can just observe here. That is what it has been written here. Of course, task code disables the interrupts. And what is the amount of time that disable interrupt whenever actually the task code, when it has disabled the interrupt, the maximum amount of time that can okay, here it is written. For disabling the interrupts, the maximum amount of time for disabling the interrupts is 250 microseconds. 250 microseconds, beyond 250 microseconds, there is no provision actually for disabling the interrupts. So even the actually 120 microseconds, now it is less than 250 microseconds. So this is not an issue. Even 250 microseconds, what we had for this timer interrupt service routine, that is also almost equal to 50 microseconds. So definitely not an issue. So that is why it has been written here. Whenever it has this is the point at which disables the interrupts. Okay, now this interrupt request has been raised. Interrupt request, this is the maximum that we can have it. The worst case interrupt latency. Now imagine actually at this point your interprocessor interrupt occurs. So it means the another processor has requested the processor for its attention. So interprocessor interrupt occurs. So that is what here it has occurred here. So we know that actually from this one the maximum amount of time that it can take is 250 microseconds. So from here to here it is 250 microseconds. So that is the amount of time you can disable that processor. You will make sure that this will not go beyond. I mean the time for disabling the interrupts will not go beyond 250 microseconds. Now when this has occurred 250 microseconds, what is the amount of time that interprocessor service routine will take it? Interprocessor interrupt service routine will take 300 microseconds. This is what we have seen it here, isn't it? The interprocessor interrupt routine takes 300 microseconds to execute. Now in this case actually 300 microseconds. Now this starts here. So that's what processor gets to interprocessor interrupt service routine. ISR means interrupt service routine. So interprocessor interrupt service routine. Now this is 250 microseconds because this is the amount of time your time is available for disabling the interrupts. So at this point your the interrupt is disabled, and assume that actually at this point only the IRQ is raised, that is the interprocessor interrupt occurs, it raises an request. So we know that actually for 250 microseconds the interrupt is disabled. So after 250 microseconds what happens here, the interrupt is enabled. So at this point actually your interrupt is enabled. So interrupt is enabled at this point. So when interrupt is enabled at this point, now what happens at when the interrupt is enabled at this point, now the processor actually gets the interprocessor ISR because there is a pending request. What is a pending request? Because there is this interprocessor interrupt occurs at this point, so this request is pending at this point also. Since you have disabled the interrupt request disable the interrupts for 250 microseconds, after 250 microseconds you are enabling the interrupts. That's what has been done here. See here, disabling and enabling. So after enabling, when you do the enabling, definitely this pending request will be taken and it will be processed. So that's what you have 300 microseconds. When you have 300 microseconds, so definitely this addition of these two things, when it started, when the request was raised, when the request was raised at this point, so 250 plus 300, so total what you get is 550, which is less than 624 microseconds, because 624 microseconds when another processor has raised the interrupt request, it has to be answered within the 624 microseconds, and definitely at this point 250 plus 300, which will be equal to 550, that is less than 625. So the request has been answered. That is how actually this is the worst case interrupt latency that we took this example. Okay, imagine actually what happens actually if the processor is running at half the speed. When the processor is running at half the speed, now what happens actually, but the deadline remains same. Deadline remains same, that is 625. So deadline remains same, but the processor is running at half the speed. When the processor is running at half the speed, so 250 microseconds instead of 250 microseconds, how much time it will take? It will take 500 microseconds for disabling the interrupt, because it is twice. And how much this takes? Actually 300 microseconds to service the interrupt. This will be doubled here, because processor is running at half the speed, so definitely you will have 600 microseconds. So now what happens? 500 plus 600, total it will be 1100. 1000, don't you think 1100 microseconds is less than 625 microseconds? This deadline will not get doubled here, isn't it? So 625 microseconds. This one example was taken, another example where if the processor is running at half the speed, now we can understand that the deadline is not met. Okay, so hope you got this point. So this is worst case interrupt latency. Just one example was considered here. Let me take one more example, same thing. Now what happens in this one also, worst case interrupt latency, same thing only. The only change what has been made here is that, so here actually I have added one more interrupt here, that is actually the network interrupt. Okay, so of course here it is the network interrupt. Now let us assume that actually for this 250 microseconds, first same thing, 250 microseconds is the maximum time the system allows for disabling the interrupt. So 250 microseconds, so here task code disables the interrupts. We know that actually till 250 microseconds, even though the interrupt request is raised, see there are two interrupt requests which have happened between within this 250 microseconds. One is the interprocessor interrupt occurs at this point, that is at this point, otherwise network interrupt occurs at this point. So at this point interprocessor interrupt occurs, at this point network interrupt occurs. So what happens here is that both these two interrupts will not be considered. When they will be considered? Only after enabling the interrupts here. Only after enabling the interrupts, both these two interrupts request will be considered. Of course, there are two issues. One let me take first case, that is interprocessor. Let me write it as interprocessor interrupt, that is IP. IP priority is greater than network interrupt. Okay. Priority interprocessor, let me write IP interprocessor interrupt, that is greater than network interrupt. So when priority of the interprocessor interrupt is greater than network interrupt, now what happens here? Of course, in this diagram actually it has been shown in other way, the second case. Let me write it here. For this case actually what happens is that now in this case what happens, see here, now 250 microseconds what you have here, this is 250 microseconds now plus. So what happens if this, okay, after enabling the interrupts, both these two pending interrupt requests will be there, but now since interprocessor interrupt priority is greater than network interrupt priority, so that will be considered first. So now there won't be an issue because this will be considered first, 250 plus 300. Now we know that what is the deadline that we have for the interprocessor interrupt, that is 625. So but these two addition what we'll get is 550. So 550 is definitely less than 625. So there won't be any issue with this interprocessor interrupter. Now but what happens actually if second case which has been shown in this diagram. So if priority network interrupt is greater than IPI. So network interrupt is greater than the interprocessor interrupt request. So when network priority is greater than IP, that is interprocessor interrupt, this is network interrupt, this is interprocessor interrupt. So when this priority is greater, now what happens, that is what it has been shown here. After enabling of the interrupt, when the time gets over, now what happens in this case is that processor gets the network ISR. Why it will get to the network ISR? Because this priority is greater here. So definitely it will get to the network ISR. The amount of time, so let me take for it is, in this case it is 100 microseconds. So 100 microseconds is the time taken to answer the network ISR. Okay, so answer the network interrupt request. So means the amount that is taken to execute in the interrupt service routine, that is 100 microseconds. So 100 microseconds gets elapsed here. So 100 microseconds gets elapsed here. After this network ISR gets over, that is network interrupt request is considered. So next thing what is taken is this one, the interprocessor ISR. So when this interprocessor ISR is taken here, you can just observe here. So this is 100 microseconds. When in this, at this point the processor gets to the interprocessor ISR. So this amount of time what it takes here, 300 microseconds. In the last one we took it. So in this case, what is the total amount of time that happens here? 250. First it has to wait for disabling the interrupt. Next one what it takes is 100 microseconds. The next one what it takes is 300 microseconds. So this will be equal to 250, 350, 300. So you will have 650. So you will have 650. 650 is definitely greater than what you have here is 625. So 650 is greater than 625. Now what do you mean by this one is, your deadline is not met here. So since 650 is greater than 625, the deadline is not met. So what do you understand from this one is, so here whenever the it also depends on the priority. So in this case actually the priority, first case the priority of the IPA was greater than NI. So that time actually, since for this case the IPA is taken first, that is the interprocessor request is taken first. So that's why it has met before the deadline. Whereas in this case the network interrupt is taken first. At that time actually it is not able to meet the deadline, because first it has to answer this one, next it is going to answer the interprocessor request. First it answers the network request, then it is going to answer the interprocessor request. So definitely it is going to go beyond the deadline. That is what we observed here. So it also depends on the request priority, the priority what is set for the various interrupt request. Of course, this is what is interrupt latency, how the interrupt latency is measured and all those things. So let me take you to one more slide. Okay, last class actually, so this is the disadvantage what we had with the disabling the interrupts. Of course, disabling the interrupts, what is the problem? Why did we go for the disabling the interrupts? We went for disabling the interrupts. The one main thing actually what we had for, it was solving the shared data problem, isn't it? Shared data problem was getting solved, but this was advantage that we had. But what was a big disadvantage that we had? Disadvantage was, it was increasing the interrupt latency, isn't it? It was increasing the interrupt latency. Why it increases the interrupt latency? Because when you disable the interrupts, whatever the interrupt requests that are there, so they have to keep on waiting. they have to keep on waiting for enabling the interrupts. When you enable the interrupts only, those interrupt requests will be considered. If you do not enable the interrupts, then there is no use, those interrupt requests will not be considered only. So, interrupt requests will be considered only when you enable the interrupts. So, that is why this disabling the interrupts will increase the interrupt latency. So, interrupt latency is increased here in this case. So, that is one disadvantage that you have it here. So, in order to overcome the disadvantage with the disabling the interrupts, we have one more alternative method that you have to solve the problem of the shared data problem without actually disabling the interrupts. It is similar to the previous problem only. So, what is taken here is that whenever actually you read the values, you do not update the values what you have read the values. Okay, we will discuss that one in this slide itself. See here, of course, in the earlier case actually we discussed only one, we declared only one variable, I temperatures or A of 2. Okay, here in this case actually we are declaring one more variable, that is I temperatures B of 2. Now, of course, static boolean, this is boolean, you have written f task code using temps b is equal to false. This variable has been taken here. So, this is false. Okay, first you declare this one as false here. Now, you can just observe here void interrupt we read temperature. This is basically what you have here. This one is interrupt service routine. So, let me write interrupt routine only. So, interrupt routine. Now, here f task code using temps of b. So, in this case it is false here. So, you are not this value a will not be updated else. So, b will be updated here. For initial case this is false. So, this will be updated. Now, let us actually see that one. So, first let us take with an example. So, what is this one? This what you have here is this one is task code. Now, what happens while of true if f task code using temps b. Now, in this case actually you have first initially defined universal declaration has been done here. So, this is basically the false. So, if f task code using temps b, this is false here. So, it will exit from this loop, it goes here else if temperature. Now, what happens here is that let me actually see this one. See, we have already discussed this one in the last video. So, this is basically even though actually this is a single statement, but this will be updated with the register R1, isn't it? So, this is register R1, this is register R2, this is register R3, this is register R4. So, let me write it here only. So, let me write R1, R2, R3, you have R4. Okay. So, R1, R2, R3, R4. Now, what do we have here is that, of course. So, what do we have here is this. Now, imagine actually first your temperature value that is read is 74. So, when it is read 74 at certain T1 instant, 74 is read. So, A of 0, that is temperature of A of 0, that is since here see you can just observe here, this is f task code using temps b is false here. So, whenever it is false here, so it comes here. Imagine actually temperature of A of 0, that is read to be 74. So, when temperature A of 0 is read to be 74, now interrupt occurs. So, this is read to be 74, interrupt occurs here. So, whenever actually, so because see while of true if f task code using temps b, earlier actually do not actually worry about this one sir here, if f task code using temps b, this is false here. So, this will not be updated, do not worry about that one. Initially actually your temperature A it is reading, let us assume that one, okay, because the task code is run first, always task code is run first, it is not actually interrupt. From the task code it goes to the interrupt service routine, then returns the values, then task code resumes. So, here let us assume that if f task code using temps b is false here, so it is false here. So, this will not be executed here, it comes here. So, let us assume that temperature of A of 0, the reading is 74, that will be stored in R1. Okay. Now, interrupt occurred. Okay. So, at T2 instant the interrupt occurs and the temperature is going to be read here. So, temperature is going to be read here. Assume that temperature A of 0, temperature of A of 1, same problem what we discussed in the last video, both are updated to 75, both are updated to 75. Now, just understand the point here. Now, Now, of course, what is going to be updated, that is what you have to understand here. Okay. Let me just erase this one and explain it. See here. Okay. So, first initial case while of true, if f task code using temps b, now it is false here. Now, this will not be read here, it comes here, temperature of A of 0, first at T1 instant it is 74. Okay. This is what you are reading. So, you are reading from the temperature A of 0. So, your R1 is containing 74. Now, what happens here is that now interrupt is raised here. Whenever interrupt is raised here, before A of 1 gets updated to R2, here temperature of 0 is getting updated to R1 here, but temperature of A of 1 is still it is yet to be updated to R2. Before it gets updated to R2 here, now your interrupt request occurs from the hardware. Whenever interrupt request occurs from the hardware, now you just observe here what is going to be updated, because here f task code using temps b is false here. So, what is going to be updated? Your temperature of B of 0 and temperature B of 1, these two are going to be updated. So, at T2 instant, what is temperature of B of 0? Temperature B of 0, this will be 75 and this will be 75. Okay. So, earlier I had said temperature A of 0 will be updated 75. No, I am sorry. So, here temperature B of 0 is going to be updated 75, temperature B of 1 is going to be updated to 75. So, earlier case, let us assume temperature A of 0 was read 74 and temperature A of 1 is also going to be read 74 here. Now, what happens here? This is the beauty of the program here. Now, when this temperature B of 0 is going to be updated, temperature B of 1 is going to be updated to 75, 75. Now, when it resumes the action from the task code, when it returns here, now tell me what is going to be stored in R2 here? Temperature A of 1 reading. What was temperature of A of 1 reading? It is 74 only. Now, at T1 and T2, 74 and 74, so both R1 will be equal to R2. So, there won't be any change in this value, alarm will not be set. This is the beauty of this program now. See what happens here is that now when it actually goes, now of course you are going to update, this is very important here, because you have gone to the interrupt routine. What you are going to do, f task code using temps b is equal to negation of f task code using temps b. Now this is negation of false here. Now what is set here? True it is set here. So whenever it is set true here, if this is going to be true, now what is A of 0 is going to be updated. But now when let us come here, this is going to be true, it will not go directly here. Void main void while of true. Now if f task code using temps b, now it is true. Now it is true, but now the reading should be, what should be the reading? Because at T2 this 75 was there, so definitely this 75 has to be considered, isn't it? So the temperature has to be updated. Now this is true here, so it comes here. Now R3 will be containing, both R4 will be containing 75. Imagine actually at this point, imagine one more thing. Now let us see, 75 was getting updated to R3. Now again interrupt occurs at this point. If it happens, what happens? R3 now it is containing 75, but R4 still it is not updated to 75. Still it is not updated to 75. Before the updation of the R4 to 75, some interrupt occurred here. When this interrupt occurs here, now what happens? So what is f task code using temps b here? Now it is true. So again it will go back here. Now if f task code using temps b is true here, so what is going to be updated? Now you just observe here, temperature A of 0, temperature A of 1. Imagine at some, whenever interrupt occurred, let us say 3 occurred, temperature A of 0, now this will be updated to the newer value. Let me take it as 76. Temperature A of 1 also let me take it to be 76. Now these two values are updated here, but are they going to be read here? No. That is the important thing here. When interrupt when the task code resumes here after returning from the interrupt service routine, what is going to be read into R4 here? The R4 actually, of course, if I have to write it, let me take this is writing and this is reading. Okay, what is going to be written into R4 here? This, the older B1 value only, the older B1 value only, which was not updated, which was not read here, isn't it? So the older value that will be written into R4 register. What was the older value? That was 75 only. So 75 will be contained in R3, 75 will be contained in R4. So there won't be any issue, the alarm will not be set. But one thing what you have to understand, since you have actually accessed the routine here, again f task code using temps b is equal to negation of f task code using temps b. Now what happens here? Negation of true here, again this will change to false here. When this gets changed to false, while of while of true, this is fine. Now if f task code using temps p, what is this one now again? Now this is false here. When this is false, this won't be updated, it comes here. Now temperature, now this is R1 A of 0, R2 A of 1. What is A of 0 new value, that is A of 1, that is 76. Now R1 will be updated with the 76, R2 will be updated with the 76, both are same only. So again the alarm will not be set. So we are avoiding the false alarm by using this extra variable temperature of B of 2. The one thing that you have to understand here is that how we solve this problem without disabling and enabling the interrupt. The problem was solved because whatever you write it here, the same thing you are not going to read from the hardware when the interrupt occurs. You can just observe here. See, whenever f task code using temps b, what are you writing here? Writing into the registers. Okay, b of 0, b of 1. But whenever this is false here, okay, if I just come here, when this is false, what you are updating here? A of 0 and the A of 1. This is just the opposite of this one. If you just observe here, whenever this is true, this comes B of 0, B of 1. But whenever this is true, A of 0 and the A of 1 comes, isn't it? Whenever this is false, this one A of 0 and the A of 1 is being written here. Whenever this is false, B of 0, B of 1 is being written. So in summary, what I can write is that what values are written in task code okay, let me take what variables. What variable values are written in task code? Different variable values are read from hardware in ISR. See, this is very important that you have to understand here. What variable values are written in task code? Different variable values are read from the hardware in the ISR. You can just observe here. Whenever actually f task code using temps p is true, you are actually writing the content of B of 0 and the B of 1 into R3 and R4 here. But whenever actually f task code using temps b is true here, whatever reading from the hardware, it is A of 0 and the A of 1. Similarly, when f task code using temps b is false here, what are you writing A of 0 and the A of 1 into R1 and the R2? Basically that A of 0 and the A of 1 is being written into R1 and the R2, isn't it? Of course, whenever actually this is false here, what are you updating? B of 0 and the B of 1, that is reading for value from the hardware here. Basically B of 0 and the B of 1 you are reading from the hardware here, but the updation actually, that is A of 0 is getting updated to R1, A of 1 is getting updated to R2. So this is how actually you do here. What variable values are written in task code? Different variable values are read from hardware in the ISR. That is how we solve the problem of shared data and and also interrupt latency is not increased. Now interrupt latency I can write it as not increased, because you have not written any enable disable interrupt and the enable interrupt. You are not disabling the interrupts. When you have not disabled the interrupts, then interrupt latency is not going to be increased, isn't it? So interrupt latency will be solved here. Of course, the increasing of the interrupt latency problem is solved here, and also the shared data problem is solved. So this is a way that if you write this one without disabling the interrupts, both these two problems are solved. Okay, the technique is what variables you are updating in the task code whenever, so with the same flag, with the same flag value, what variables you are updating, the same variables are not going to be used in the interrupt service routing with the same value of the task code, that is flag value of the flag value task code which I have taken here. Okay, so whatever values you update in the task code by using the flag, the same flag value you update in the interrupt service routine with the different variables, so that the problem of the shared data as well as the interrupt latency is solved. Okay, so this is how you do. Of course, you write the program to disable the interrupts without without incurring the extra interrupt latency. Okay. So, hope all of you understood this one. Fine. Thank you.